Well, I think one can say that the brain is responding to the external environment and to the internal environment at all times, because nerve cells are designed to receive stimuli, somehow store information, and transmit information. So their mere nature requires that they receive input from both the internal and the external environment at all times. And we've shown that we can change the brain both internally and externally from internal and external environments at any age. Admittedly, the brain is growing most rapidly right after birth. I was just going to say this explosive development of fibers, because I usually use my hand. It makes a perfect nerve cell to start off with, and as it receives stimuli, it grows its branches. And this is what is happening in those first years after birth, is the development of the branches, which are the main receptive portion of the cell, and forming connections with other cells. At the present time, in general, neuroscientists say that there are 100 billion nerve cells in a brain. And many of those nerve cells can make connections with thousands of others. A single nerve cell can receive as much input from about 20,000 other cells. So you think of the computation that goes on in a single cell before it fires. So the interaction of the environment with this system is extremely dynamic and important. Well, I think essentially this is what learning is. It's making new connections. We know that protein synthesis takes place during learning, and nerve cells are made of protein, so that we're growing these branches while we're learning. We've been able to show this in the laboratory with our rats, learning to solve mazes, and then we measure the cells afterwards and find more branches on those cells that have been challenged and are learning versus those cells that are very inactive. Endangered minds. No, I think she's expressing some of our concerns with the modern day child who sits in front of a television for hours. And even though we know some learning is taking place, it's the passivity for most children that is so detrimental, because again, in the laboratory it's been shown that those rats that sit and watch other rats play, only the rats that are playing show changes in the brain that we can measure. The rats that are sitting and watching the others play, their brains don't change. So we think it's a total activity of the body, both physical and mental, to bring about these changes. Well, when we first showed, this was way back in 1964, and presented our work, I remember one man stood up and said, "I'm sorry, but the brain cannot change." And I said, "I'm sorry, but we've been able to show that it does." And now in the scientific world, most people say, yes, the brain's like a muscle. You use it, you don't get new nerve cells, but you do get larger nerve cells. And that includes the cell body and all of its branches and connections. We live in a multisensory environment, and the brain is designed to receive many types of sensations. And while it is developing so fast, we should be giving it the opportunity to utilize this kind of input rather than single-track an input. So I think it's very important as we watch modern technology coming in where we might want to focus children in single channels to still see that we have olfaction, we have taste, we have sight, hearing, multisensory, and get this whole cortex to grow and develop so that it's ready to handle the problems in this complex world, rather than give them narrow, focused learning. We've found with the brain certain parts are extremely plastic, extremely changeable. Other parts are not. And many of the older parts of the brainstem do not change. They're closer to, to what you call hardwired. And we've taken all the brain into 15 different parts to see what's moving and what's not. And these older areas don't move as readily as do the more recently evolved, such as the cerebral cortex. It seems to be the most plastic of all. It's true when the brain has evolved, that it's evolved up from the spinal cord into a brain stem. And again, the hand can be very useful. And then onto this brain stem, we've added these massive hemispheres. And the hemispheres account for 85% of your brain. Yet it's these hemispheres that we find are most changeable. We do not find this basic brainstem is as changeable. It's dealing with more basic, fundamental functions such as appetite and thirst, sexual behavior, temperature regulation, heart regulation, respiration, fundamental functions. But the higher cognitive processing is taking place in the newer mass. And that's where we find we can change so readily. We can change in our rats this cerebral cortex structurally in just 4 days and measure the increase in dendrites in 4 days. Well, we can show that it will go up in 4 days, but it'll also come down very quickly with disuse. So one has to stress the importance of use versus disuse. But then again, one has to ask, what is use? The pediatricians are concerned that the modern mother is giving too much stimulation, and the children will cut it off. So we bring in this word of common sense, that we know when to stop. We've heard enough of somebody. We say thank you and we walk away. But what does the child do? Because mother is constantly saying you need more. They will cut off later in life. So you need time for assimilation. When information is coming in, it comes into the primary centers first. For example, vision. I first see your green shirt. But then to think about a green shirt and what it means, that goes into my association cortex. Children need time to associate. Adults need time to associate. When I teach, I always write on the board, because I say it, the students hear me, but they don't have time to put it into their association cortex. By writing on the board, it slows it down, they can think, and at the end of the lecture, they know what you said. Well, a question that we've asked for many years is, what is enough stimulation? And does the brain have a ceiling? Will it continue to grow with stimulation, or will it stop? And so we designed an experiment where we change the toys for our rats much more frequently than we normally do. We normally change them twice a week because the rats like novel stimuli just like we do. But this time we changed the toys at night, at 7 o'clock at night, 8 o'clock at night, 9 o'clock at night, for 4 nights, for 4 weeks. And we found that we didn't continue to increase the brain. The rats just didn't interact with the toys as much when we were changing so frequently. And I think it's the same with children. You get too much in a room, they don't know how much to accept, therefore they don't really interact much with anything. You give them 1 or 2, they're hungry, they're curious, but then they play with it for a while and get bored and want something else. So I think our rat work has taught us a great deal in how the brain changes in response to the amount of stimulation. Well, I think one says that these people who believe in the spurts were saying that the brain grows and then it stops for a while and then it grows again and stops for a while, and one should either educate while it's growing or educate while it's stopping. I never was quite clear on which. But I can say that we have measured the growth of a rat brain in various environments where one can make very precise measurements. And we do not show these growth spurts. We show that it's a steady incline, very rapid right after birth, slows down a little bit but continues on, and then reaches a peak and then starts to go down. And this correlates very nicely with Professor Chugani's work at UCLA, where he was using deoxyglucose uptake with human infants, and showed that the deoxyglucose uptake right after birth is very rapid in the outer layers of the brain until 2 years of age, continues up till 5 years of age, not quite as rapidly, then continues still climbing, but slower, till 10 years of age, and essentially reaches a peak at 10 years of age. So it corresponds very clearly to what we see with this rapid growth, continuous growth, during these early periods. Well, as I mentioned earlier, the nerve cell is designed to receive stimuli. And so once we have a nerve cell, we've been able to show that it can. We've shown that we even can measure increases from brains from mothers that have been living in enriched environments. So we've shown a prenatal increase, an early postnatal, young adult, middle-aged, and very nicely, extremely old age, equivalent to 90-year-old people. 900-day-old rats are very old rats. But we've still shown, if we put them in enriched environments, roughly in middle age, and then follow them to equivalent to 90-year-old people, that we can change that brain. So this is very optimistic toward education, toward life in general. When people used to give up and say, well, I'm over 40, why should I try so hard? We're saying try so hard for your full 100 plus years, because the brain has the capacity, providing it's healthy. We're not talking about disease brains. That's another story. We are a total human being. There's a reason for being wrapped in this skin. We've evolved with many systems of the body, each one dependent on the other. We talk about the brain so much because it is this phenomenal structure that is unique to each individual. I can get a liver transplant and survive. I can get a heart transplant. But if I get a brain transplant, I'm no longer myself. And it's one of the best lessons in self-respect for anybody is to tell them that his or her brain is unique on this earth to develop as he or she sees fit. But we talk about a central nervous system, which is the brain and the spinal cord. But for this unit to talk to the rest of the body, we have a peripheral nervous system going out to the limbs and the rest of the body. So all are working together. And we have an autonomic nervous system, which is keeping my heart going while I'm talking, or my breathing taking place, and things I don't have to think about. But at all times, these are integrated into all systems working together. Terribly important that you damage one, it influences the effects and the function of the other. There's evidence from UCLA, from Dr. Arnold Scheibel's lab, that shows that in adult schizophrenics that for one reason or another have passed away so one can examine the brains, that there is an abnormal appearance of the nerve cells in this hippocampal region deep within the temporal lobe. And as one goes back to development, those cells normally migrate into position during the second trimester of development. And there is evidence from a Finnish study to show that women who had a certain virus during that second trimester had more cases of schizophrenia. But this is giving some credence to the fact that such a disease as schizophrenia may be due to abnormal embryological development. But it gives a perfect example to what you had said. I would like to say something, however, that I'm so interested in the moment, because I think it's so important, is the prenatal diet. When we were teaching in Africa, the mothers did not want to eat protein while they were pregnant because they did not want to have large babies. It was too difficult. I said, what are you doing to those brains? After doing experiments on these now with rats, one can show that if during pregnancy that the mother has a low protein diet, those little brains that are formed do not respond to enriched environments. And so I play this in conjunction with Head Start, because if we're going to put hundreds of millions of dollars into Head Start, which begins 3, 4, 5 years of age, if we haven't developed the appropriate brain to receive that education, it'll be a waste of money. So it's important, equally important, to be sure that the brain has developed well in utero. So when you start with the education, you have the nerve cells and the dendrites to respond to that marvelous education. I think that an impoverished environment during the development of the fetus is very detrimental to the brain for a lifetime. Because if we don't form the nerve cells appropriately, they're not making the right connections early, and then when we try to educate and work with them, we don't have the basic material to stimulate. And that has been shown very clearly with protein-deficient diets, to say nothing of cocaine, alcohol, other much more abusive substances that are reaching these brains, and these will be children that will be faced with educating in the future. So I think our education should come very strongly for prenatal health care, to be certain we give these infants a good chance. Nobody really thinks about brains. They don't think where behavior comes from. And I think the more we understand about brains, the more we'll understand each other as a same sex, as different sexes, and working together, and people who have different sexual preferences. For example, Fleming up at Brigham Young University stressed the pregnant female rat. Those male pups at birth, baby rats are called pups, did not have the normal right greater than left. They had the female pattern. And when those baby rats grew up, they behaved more female-like sexually. And so there's a biological basis for our preferences and how people cry out to be understood, why the little boy prefers other little boys and keeps it quiet because he doesn't know why. But the more we learn about sex differences in the brain, the more we can understand all of our types of human interactions and behaviors. I think that it comes to how the impact is laid down in the brain. Because we know, for example, if we're in an automobile accident, we never forget it. The adrenaline is high. Somehow the adrenaline embedding that memory is stronger than if we have something very mild in contrast. So the more stress that's related to the experience seems to allow it to embed for longer periods and for stronger periods of time than with something more modest and mild. Let me again speak about my rats, because if we put little rats in the enriched environment with their mothers before their eyes are open, but yet they have access to toys to play with, we're not forcing them to interact with those toys, but they have the freedom to explore them on their own. We can accelerate maturation by doing this, even though they don't see them. So yes, giving the opportunity, but the teaching that would come in and the parental dominance in directing is another matter. Because is that brain ready to receive that additional stimulation at that time? That we're not certain. But I can say, when given them the free opportunity to pick these things up, maybe the mother would be playing the piano off in the background. The child wants to come play and climbs up on the stool and gets taught, versus the parent forcing it. They're two different responsibilities to that brain. Keep a healthy body, keep a healthy mind as much as you can during this period. But as I've said with our own work, protein in the diet is terribly important. Vitamin B is terribly important for the development of the brain. But exercise is healthy because we're a total body, to keep the placental circulation active. Stay away from stress if possible. The Japanese have said it for 2,000 years, Taikyo. Think pleasant thoughts. It's not always possible, but recognize that what you are doing will influence the development of your infant. And as much loving care between parents as possible, and with your child as it's developing, even if it's in utero. I think it comes into the electromagnetism of the bodies, and some give off more of a positive essence than others. And animals can pick it up, children can pick it up. We don't understand how to measure it. We were talking about this out at Livermore at lunch today, about how to measure these kinds of things that we're giving off, and thought waves as well. We don't have the apparatus to pick these up yet, but our children sense, we know just as adults know, which person we want to interact with as to the flow of energy amongst us. So there's a lot of room for discovery ahead, and instrumentation will be refined so that we could measure these things in the future. We know they're there, but, and as I asked Isaac Asimov once, when he had an idea in one of his books, and I wrote him and I said, "How did you get that idea?" He said, "Much more can come out of a brain than goes into a brain, because we have certain parts that are just talking to each other. The right and left sides are talking to each other, and within each side the parts are talking to each other. So once we get information up there, the potential to interact is tremendous, and that's the thrill. But that's the part that we can't measure too well. But we do show, again with our rats, that in a nerve cell, it's receiving information different branches receive from different parts. Some are receiving subcortically, some intracortically. And we find with our enriched environments that the branches that are receiving intracortically are growing more than are receiving subcortically. So once the information gets up there, it's having a lot more fun than the information that's just coming in. I think if I were to start to help children have more creative brains, I'd get a group of them in a room and give them the basic fact. I'd hold a human brain in my hand and say that no two human brains are alike, ever. Each one of you is an individual. And I'm going to give you each a question, take you to a separate room, and tape your answer. And then bring all of you back and let you hear how each one of you have handled this answer. See what the similarities are and what the differences are. And then see how you can learn to use knowledge to come and achieve new knowledge. And work with your basic facts for new ideas. And for some reason, somehow, new ideas are some of the most satisfying experiences in our existence. And every child should have the experience of getting new ideas and knowing that it's his own or her own. Because this goes on for a lifetime. I think we certainly can. And I can say this morning I got up at 5 o'clock to look at some new data and found something brand new and had just the same thrill that I did when we did our first experiments 30 years ago. So the thrill of discovery can last a lifetime, and that's one of the greatest things we can teach children, is to seek new knowledge, to retain curiosity, to be asking questions.